To help us understand what building a financial model looks like, I've assigned my systems engineering students this project problem about whether to buy a snowplow. The idea here is that the plow costs $4,000 to add to an existing pickup truck, and the owner of the truck has to borrow the money in a loan. They need to know a few things: the interest rate they're going to pay on the loan, the hourly rate they will be able to charge customers for the snow plowing service, and the wage rate that they're going to pay the driver. If they're driving, I suppose the wage rate that they expect to collect themselves. Finally, we don't know how many total hours they're going to be able to build. Will it be a winter with a lot of snow or just a little bit of snow? And so all of these uncertainties can be explored in a model. And Excel is a terrific tool to allow us to do that. So I've copied the problem into this Excel sheet, and I want to help my students understand how to set it up. The first thing that you got to do is have a sense of the expected cash flow diagram. Let's set some parameters up at the top. In this set, I'm going to call these months and attempt to create a cash flow diagram. For example, the first thing, month 0, you got to come up with $4,000 to buy the plow. And we know that that money is going to come from a loan. So if it's a 0 money down loan, at time equals 0, there's actually no cash outlay. Then for the sake of convenience, we have to have some expression of how much the driver of the plow is going to collect. And we'll say that it corresponds with the end of the month. That is, he plows the driveways and he bills his customers, who all pay their bills at the end of the month. At the same time, he's got to pay the loan for the plow at the end of the month. So it would be very helpful to be able to compute the loan payments and know what they are and record them here. Fortunately, we have an equation. We're going to use the equation that we learned in class. P equals A times 1 plus the interest rate raised to the power of the number of compounding periods minus 1, all in brackets, and divided by the interest rate. I'll use some more brackets, divided by the interest rate times 1 plus I raised to the n, the number of compounding periods. So this is what the equation looks like. I'm typing it out here because in Excel, equations are often difficult to interpret it, and we have to rearrange it. Remember, this is the present value, and A is the series of payments, the equal series of payments over the life of the loan. To solve for A, we have to, of course, divide both sides of the equation by A. We have to do the algebra and rearrange it. So what are we going to get right here? Equals the amount of the loan. We're going to need a figure. Let's choose this cell, in which we're going to put in the loan amount of $4,000. The monthly payment, if we make 6 equal payments, is going to be that $4,000. We'll need an interest rate. And remember that the interest rate must be expressed in the same unit of time as the compounding period. So here's the loan amount in dollars. We're going to do a little formatting on that. And then here's the interest rate, 0.01, which is sort of convenient. interest rate on the loan in percent per month. Boom. So now I can reference these cells when I say it equals the loan amount times the interest rate times, gotta open some brackets, 1 plus the interest rate raised to 6 compounding periods divided by 1 plus the interest rate. I'm going to need 2 parentheses on this one. 1 plus the interest rate raised to, boom, the number of compounding periods minus 1. What's the monthly payment? $690. Because that payment is going out, I'm going to call it negative. And I can copy this all the way across here as long as I lock in some of these cells. As long as I keep that column the same when I copy, that column the same when I copy, etc., etc. So now what I've done is I've computed the loan amount. The amount billed to customers is going to be different. Let's build out that part of the model. We have a billable rate for plowing in dollars per hour. And let's say that we can bill $80 per hour for the sake of argument. We got to have the number of hours per month billed. How much snow is there going to be to remove? And suppose that's going to be 100. Then it would mean 25 hours a week. Maybe that's a couple of storms and a bunch of customers. The amount billed, going to keep track of some units here. Loan payment is in dollars. Amount billed, both of these actually in dollars per month. Here we have the billable rate, dollars per hour, times the number of hours per month. Boom. And I'm going to lock in these columns. That's the revenues. And we have some costs. Remember, we're ignoring depreciation on the truck. We're just talking about the wage paid the driver. And that's going to be in dollars per hour. Let's say it's 30. Now, the wages paid driver, dollars per hour, goes in this column. Boom. It's going to equal the number of hours billed times the hourly wage paid the driver, and you know it's going out the door, so it's negative. I'm going to copy that over. So far in this problem, the net cash flow is going to be, again, neglecting the depreciation of the truck, which we'll talk about in another video, $4,310 after paying the driver, after paying the loan. It looks like it's a pretty good business. What we haven't done yet is compute the net present value of this business. And that means that we're going to have to adjust each one of these future incoming, this net cash flow into a present value. We will make a separate column for that. This present value is not dollars per month. It's just in terms of dollars. And to do that, we're going to take that future amount divided by 1 plus the interest rate raised to the power of the number of compounding periods. Boom. You can see that I've missed a 1. Corrected. We don't need all of these decimal places. And so how do we reduce them? Just like this. We're going to the nearest dollar. You can see that the amount that the present value of this 4,310 collected at the end of the first month is less than 4,310, which makes total sense. In this case, we are using the interest rate as a discount rate. That is, the interest rate on the loan we've set as equivalent to the discount rate that we would use to compute the present value of some future amount. So this is the present value of each individual month calculated by converting the future value to the present value using an equation that is familiar to us. I'm going to change the font size to 14 for the sake of consistency and legibility. The net present value of the entire project is going to be the sum of each one of these months. So I suppose that these dollars could correspond, because they come in each one, to units of dollars per month, but we're just going to sum all these up into a total net present value. Boom, boom, boom. And what are we going to find out? This seems like a pretty good business. $25,000 is the net present value of buying the plow and doing all the plowing work. That's even if you pay someone else to drive the plow at $30 an hour. But remember, we have yet to explore our model space. What we've done so far is built a model. What we haven't done is say, how sensitive is that model to different parameters? Here, I just increased the interest rate to 2% per month from 1% per month. What if it's not a snowy winter and we only get 20 hours a month instead of 100? Now, the amount that we're able to bill is far less, and the net present value of the project goes down to $1,600. What if we can't find a driver for 30 and we have to pay 50? Now we're losing money. These are good examples of how to explore the model that you built, which you know is wrong, because there is no data from the future on what these values are supposed to be. But you can explore the consequences of all of these different parameters in your model. Your task, if you're in my class, is to construct graphs that show the sensitivity of this outcome, net present value, to exploring each one of these individual independent variables in kind.